Hello and welcome to my presentation entitled Drug Release Mechanisms from Coated Pellets, How Non-Invasive Analytical Tools Can Help to Comprehend Them. I'm Susanne MUSCHERT from the University of Lille. I'm an associate professor in pharmaceutical technology. There's a paper in correlation with this talk, which has been published in the journal Pharmaceutics in MTPI journal. It's entitled Towards a Better Understanding of Verapamil Release from Colicode SRIR Coated Pellets Using Non-Invasive Analytical Tools. By simply scanning the QR code on the upper left-hand side, you can access the PDF directly. So the objective is to describe drug release mechanisms from sustained release dosage forms, coated pellets, which are actually the reservoir systems, meaning you have a drug-loaded core, which is surrounded by a release rate controlling membrane. So small amounts of drug will be released over time. This is a theoretical in vitro drug release profile. And the theory is when a patient is taking this sustained release dosage form, you will have small amounts being released over time. And since always new drug is released and drug is also eliminated from the body, you can reach steady blood plasma concentrations within the patient. So you will have less fluctuations, as it's the case with the conventional immediate release dosage form, which releases all drug, which is eliminated. New dosage form is to be taken, elimination, and so on. So you have, with these fluctuations, actually you have side effects which can occur, and also you have a less time points where you have not a pharmaceutical action. So sustained release dosage form can improve this pharmaceutical therapy and increase the patient compliance. So we prepared our coated pellets like this. First, the starter core. We had an equal mixture of lactose and microcrystalline cellulose that was mixed with 10% of verapamil hydrochloride, wetted, and then extruded through a cylinder extruder. The small cylinders have been subsequently spheronized and dried. So we obtained small beads, spherical beads of around 1 millimeter in size, which have then been coated in a fluid bed coater with a Wurster insert. So the pellet cores moving up in the fluid air stream, and spray nozzle is applying the polymer dispersion continuously on the pellets. And for the polymer dispersion, we used actually a polymer blend. We used a mixture of polyvinyl acetate, which is insoluble in water, Colicode SR, and Colicode IR, which is polyvinyl alcohol polyethylene glycographed copolymer, which is a soluble polymer. So by mixing these two, we can actually adjust the permeability of the film coating. So we use two blends. The first one is a 95-5 blend with a coating thickness of 5% weight gain or coating level. And the second blend we tested was a 90-10 blend with 10% of weight gain, 10% coating. So here you can see the drug release from these coated pellets performed in a USB paddle apparatus, a standard dissolution procedure. The drug release was always faster in acetate buffer, pH 3.5, which is actually not a physiological important medium, but for technical reasons, we chose a pH 3.5 and a 7.5 pH medium. However, in acetate buffer, in slightly acidic medium, we always had faster drug release. Nevertheless, the coating blend neither the coating thickness. In phosphate buffer, you can see drug release is slower. And generally, we have slower drug release with the 90-10 blends with a thicker film coating. So although we have higher amount of the soluble compound in the film coating, we still have slower drug release. So meaning the coating thickness in this special case was more important than the amount of Colicode IR within the film coating. Getting back to the fact that we have acetate buffer faster release, this is actually attributable to the solubility of the drug within this medium, because verapamil hydrochloride is a weak base and shows pH-dependent solubility. So we checked the saturation concentration of verapamil in different media with different pHs by adding excess amounts of the drug in small flasks, filling it up with medium. And when we had an equilibrium between precipitated drug and dissolved drug, we sampled in the surnatant and analyzed for quantitatively amount of drug dissolved. And you can see actually that the drug solubility is dropping with increasing pHs. And if you take a closer look of the region between 6 and 9.5, you can see that there is a severe drop in drug solubility. So this explains why for acetate buffer, we've got a higher drug release compared to phosphate buffer 7.4, because in acetate buffer, we have got more of the dissolved drug, which is represented here with the little stars. Only the dissolved drug is able to diffuse out of the coating, through the coating out of the device. And in pH 7.4, we've got rather crystalline drug. Crystalline drug, represented with these little cubes, is not able to migrate out of the device. So, however, if you want to interpret drug release mechanisms, especially with these small multiparticulate units, you have to not investigate only the ensemble of drug release, where you have like hundreds of pellets mixed together in USP pebble apparatus. And actually the ducted solution you're observing is the sum of the individual drug release of each single pellet. So we also did some single pellet drug release studies where we exposed the pellets to 400 microliters of medium in the small well plates. And we combined these single drug release studies also with an observation of how's the pH changing within the pellet core. And to do that, we had to do a pH probe into the pellet core. This has been done with pH sensitive fluorescence probes. So the fluorophores we used were incorporated in the core material. So we did another batch of pellets, added BCECF dextran and Oregon green. And upon contact to the dissolution medium, these fluorophores, which are very soluble in water, did dissolve, and depending on the pH, emitted a different intensity of fluorescence at specific wavelengths. So we performed this dissolution test combined to the pH determination from single pellets to observe the drug release from one pellet in correlation with its very same pH. So the pellet has been impregnated in the dissolution medium, either acetate buffer 3.5 or phosphate buffer 7.4. And at predetermined time point, we sampled the dark dissolution medium, analyzed it with spectrophotometry towards the quantitative analysis of drug release from the very pellet. And in the meantime, we did the fluorescence test and we measured the emission of the fluorescence intensity, and were able to correlate the pH which is creating in the pellet. And also we had a very transparent film coating. So we could actually measure through the coating and see what's happening within the pellet in terms of pH. So here you can see the results from this single pellet drug release, single pellet pH development test. On the upper row, you see the results for acetate buffer pH 3.5, on the lower row for phosphate buffer 7.4. On the right-hand side, I chose two pellets for each medium from the Colicode SRIR 95.5 per coating with 5% coating thickness. And on the right-hand side, two pellets for each medium from Colicode SRIR 9010 with a thicker film coating. And you can actually see that when we expose the 95.5 coated pellets to acidic medium, drug release is rather complete. The pH within the pellet is going towards 3.5. And the other pellet here is showing even faster release than the first one. So we actually have a difference in the individual drug release, which has been hidden in the ensemble of pellet release. So actually, we have a difference in the behavior between the two different pellets. So if you have a look at the phosphate buffer, when we expose the 95.5 pellets to phosphate buffer, you can see drug release is not complete. We still got remaining drug in the core, which explains also why the pH within this very same pellet does not go to 7.4, since verapamil HCl, verapamil free base, form like a mini buffer in the pellet core, so we can't reach the pH of the dissolution medium yet. The second pellet observed from this very same batch of pellets has even shown a different drug release. You can see that it's going up steadily. We finish with like 75% of drug released, but also the pH in this very same pellet goes rather towards 7, not 7.4. With a 90-10 blend-coated pellets, the difference is even more significant. You can see pellets exposed to acetate buffer do almost release all drug. The pH is going slowly towards 3.5. We're a bit above still because we've got some crystals remaining in the core. So same thing, we've got the buffer, which is created. The second pellet, however, you can see that it's only releasing the drug after 15 minutes. So here we've got a lag time, meaning for a small moment, we got no release, which has actually not been seen with the first pellet. So we've got really individual differences between the two pellets. Even more pronounced when you expose the same batch of pellets to phosphate buffer 7.4. Drug release is not complete at all. We only reach like half of the drug of the core. The pH is not going towards 7, rather around 6. And the second pellet from this very same batch is only releasing after 45 minutes. So here we've got a very long lag time before drug release onsets. And you can see the pH in the pellet is also not going towards 7.4. So what we can conclude from this is that we've got differences in drug release between individual pellets, which is actually not quite often seen in diffusion controlled drug release. And we also have some lag times, meaning we have a different onset in drug release. So this is actually needs to further investigation. For example, we wanted to know this lag time. Is it due to a water imbibe, which is causing the pellet to, the water is going into the pellet core, the pellet core will swell. And then when the pellet core swells, we have a pressure on the coating. And this might actually cause rupture of the film coating. When we've got a rupture of the film coating, all drug will be released at once, which could actually explain some of the individual single pellet release curves. So we investigated the increase in diameter of the pellets during dissolution of, once again, single pellets with a microscopic observation. And you can see that when we expose, nevertheless, the coating blend, nevertheless, the coating thickness to acetate buffer 3.5, the pellets do not swell significantly. We've got some, like here, pellet number 9, which is swelling continuously. We've got others like pellet number 3, which is decreasing in size and then going up again. Actually, these ups and downs can also be attributable to the fact that the pellets have not been perfectly spherical. So here you can see that the pellet number 5, however, is decreasing in size. So there actually, we could have a swelling, rupture of the film coating, which leads to a shrinkage of the pellet. But these phenomena were not quite significant. When we expose the pellets, however, to phosphate buffer 7.4, the pellets swell with much more extent. You can see, for example, pellet number 6 here is swelling, swelling, swelling until it reaches like 135% of its initial, 35% more of the initial size. Other pellets do swell and then suddenly decrease in size. So here we could actually have an onset of rupture. Even more pronounced with the thicker film coatings than of the 90-10 blends, where we have pellets that swell and then suddenly decrease in size or slowly decrease in size. So we could actually have, instead of having diffusion controlled drug release, we could have a rupture of the film coating, the crack formation. So to analyze diffusion controlled release, or to discard the theory of the diffusion controlled release, we applied a mathematical model. The mathematical model assumes that we've got a diffusion controlled drug release method, meaning only the solved drug is able to migrate through the intact polymeric film coating. So when we calculate, so theoretically, the diffusion controlled release compared to the experimental obtained data, we see theory and experiment fit, we've got a diffusion controlled release. If they don't fit, we've got another drug release mechanism. So let me explain rapidly how works the theoretical prediction. So drug amounts released over time are actually a function of the film coating thickness, the outer radius minus the inner radius, the solubility of the drug. So that's why we only did this theoretical prediction for acetate buffer pH 3.5, where we had perfect zinc conditions. K is the partition coefficient, which is the affinity of the drug between the polymeric film coating and the water-filled core. And D is the experimentally determined diffusion coefficient, meaning the behavior of the drug molecule within the polymeric network. So, and you can see when we predict drug release, in the case of 95.5 blends, we've got the good correlation in the beginning, but then the drug release theoretically obtained underestimates the one from the experiments. The model takes also into consideration a lag time, meaning we've got a drug-free coating through which water first needs to go into the core, which actually the lag time fits quite well, but then especially with the 90-10 blend, you can see that the theoretical prediction clearly underestimates the real drug release obtained from the pellets. So diffusion is not the primary drug release mechanisms with these type of pellets. So actually what leaves us with the theory of the cracking of the film coating, which can be observed by scanning electron microscopy. And here you can see an example for the Collicoat SR 9010 coating. And you can see in acetate buffer, we actually have some holes, cracks appearing. Also, after exposure to phosphate buffer for 2 hours, you can see cracks appearing. However, scanning electron microscopy needs to be performed on dry pellets. So we needed to dry the pellets after exposing them to the dissolution medium by vacuum drying, and this can cause artifacts, meaning we could actually induce cracks in the film coating by drying them. So we needed another analytical method to analyze if we have cracks in the film coatings, but also to see what's happening in the core. So we chose Raman spectroscopy. Raman imaging or Raman microscopy has been performed though first on pellets which have been cut to see how much drug is in the core. And the false colors depict the drug in red, the core material, lactose and MCC in blue, and the film coating in yellow. And the cross-section has been done with a scalpel. So you see after 15 minutes exposure to acetate buffer 3.5, there's still some drug in the core. After 45 minutes, however, with this very pellet, we have no more drug to be found in the core. Same for phosphate buffer. After 60 minutes, we have quite a lot of amounts of drugs. You see some holes appearing. This can actually be attributable to the fact that lactose is soluble in water and can leach out of the device. And here you see also no more drug, but also some artifacts due to the cutting with a scalpel. We actually displaced some of the film coating into the core. So the invasive technique is not very representative to analyze the film coating, but however, we get an idea of the film of the core composition. So to investigate the crack formation of the film coating, we used non-invasive confocal Raman spectroscopy. You can see the film has been totally intact before exposure to the dissolution medium. After exposure to 15 minutes acetate buffer, however, you see some holes appearing. After 60 minutes in phosphate buffer, the coating seems rather intact. After 120 minutes, however, 2 hours exposure to phosphate buffer, you can see that the coating has severe cracks and holes in it, also after 45 minutes in acetate buffer. So what we can conclude is that the importance of the pH within the pellet cores is present when you have a weak base extract because it influences drug release, that you can have crack formation in film coatings. However, the non-invasive analytical tools were able to monitor the dynamic changes in the pH inside the film-coated pellets with the fluorescence spectroscopy, and confocal Raman spectroscopy was able to detect the crack formation non-invasively. So since invasive analytical tools can cause artifacts, as it can be seen with SEM imaging, where we had some cracks we didn't know where they come from, And you also saw that the invasive cross-section of the pellets displaces the core material into the coating material into the core. So in this very case of this Collicode SRIR coated pellets, we've got drug release through cracks, and the weakly basic drug was rapidly released upon exposure to the slightly acidic medium. So I want to thank my co-workers on this, Julie Fayet, Branko Vukoslavic, Laure de Kinder, Hugues Florent, Jean-François Gossens from the University of Lille, Michael Windbergs, Florence Siebmann, and Jürgen Siebmann. And I want to thank you for your attention, and also the organizers of this conference for inviting me. So this is once again the link to the paper. Thank you.